缺美。
哦，
对啊，所以其实你可以看那个机器上面怎么说啊，因为机器上面已经对了，不是？146、1144、15，对啊。
I would like to challenge problem number 1, paper boomerang.
15题的。第一题被否决。
So I would like to challenge problem number 3, lato lato.
Lato is not on
But in the system, and the
解锁问题吗？
please.
就解锁，会解锁掉。
第二 set。
干掉6个人。
刚才是因为他们口用的
哦，已经手
解锁一个，
第3个就被解锁掉。下次就直接用系统。那全部都不行。气压性。
Okay, the recorder Nintendo Pro.
Honorable judges and fellow competitors, I am Dennis from Team Excelsior. Today, I will be reporting question number 3, Lato. This is the problem statement. Attach the ball to each end of the screen and connect the center of the screen to a pivot. When the pivot oscillates along the vertical direction, the balls start to collide and oscillate with increasing amplitude. Investigate the phenomenon. Today we will put the main focus on how is the increasing amplitude associated to the mechanism behind, and what parameters can be investigated to the amplitude of oscillation. This is the outline. First, we will introduce the preliminary experiment. We will provide observation video, qualitative explanation, and demonstration. This is a preliminary experiment. And this is our experimental setup. Compared to use manual to control the device, we use a machine like this. And this is a pivot and it's fixed. And we use Arduino sensor to track the data. This is the observation video. Okay, as you can see, the angle of between the lato-latos is increasing throughout the process. So as you can see in the chart. This is the explanation. So when the ball is going to collide, the effective acceleration will become bigger. So what is effective acceleration? So because this system is not the same speed, or it is not moving, it has acceleration. So we can not only consider the acceleration of gravity, we have to also consider effective acceleration. So to have an increasing amplitude as the problem statement mentioned. So when the ball is going to collide, the effective acceleration is going to become bigger to make the velocity bigger. And after a collision, the velocity moving up will have a lower gravitational acceleration. So the acceleration is smaller, so they can move to a higher position. And this is a theory, the motion before collision. So this is the y-axis and this is the s-axis. And the y-axis of the pivot point can be calculated like that. And this is the velocity, the acceleration of pivot. And the a is the amplitude of the pivot. And the omega is the angular velocity. Next is the ball's oscillation. And it could be calculated like this. So the motion before collision is this. And this is a non-inertia frame because it has acceleration. And this is the theta angle. And the acceleration of theta angle will be equal to negative the length out of the effective acceleration times sine theta. And the effective acceleration will be equal like this. And previously we mentioned the acceleration of the pivot point, and we bring it into this formula and it will look like this. And this is the theory when the ball collides. So the speed, before collision, the speed like horizontally like this will be L times the angular velocity times the cosine theta c. And after the collision, the speed will be different. So we need to time an e, which is the coefficient of restitution, because it is not an elastic collision. So the velocity will be different. And this is our experiment. We are measuring the theta angle, and we use the this is the distance between this the ball and the pivot, and this is the y-axis distance. So we can calculate out the theta angle. And next, we have to make sure the length of the string maintain the same. So the length of the string equals to this. And we can use tracker to track the length of the string during the process. And this is our data. For the 9 cm, 12 cm, and the 15 cm, the length maintain the same. So it is consistent. And next, we move on to our coefficient of restitution. Since we mentioned in our theory, the collision velocity is not going to be the same like before and after collision. So we calculate the coefficient. So we divide the velocity before collision by the velocity after the collision, and this is the coefficient we calculate. And average is 0.85. Let's move on to our experiment. Our parameter is the oscillation frequency of the pivot. And we are controlling the string length to 9 cm. And we are measuring the angle, which is the theta angle. It symbolizes the amplitude. Because if the theta angle is big, the amplitude is big. And this is the experimental data from the length of 9 cm and the pivot frequency of 3 Hz. And it has an increasing amplitude. After we point out the peak, like the highest amplitude, and this is a fitting line. When the fitting line shows positive correlation, it means that the angle of theta increases and the amplitude also increases. Next, since we mentioned about effective acceleration, we talked about when this is the angle, when the ball reaches its highest amplitude, the effective acceleration will be very low. And when the theta angle reaches its minimum, the effective acceleration will be very big to increase the velocity of collision. Next is our frequency of 5 Hz. Compared to the previous one, this one has a decreasing amplitude. And after we point out the peak and make it to a fitting line, it shows the negative correlation, which the angle of theta is decreasing and the amplitude is decreasing. And also, we compare the angle to the effective acceleration. And as you can see, when it reaches the highest amplitude, the effective acceleration will be the smallest. And after we did all the frequency of the pivot point, we can draw the slope of different frequency. So as you can see, like the frequency of 3 Hz, the slope is positive, and the slope of 5 Hz is negative. And when the slope is 0, it means that either the amplitude is maintaining the same, or we are unable to consider the amplitude. And the effective acceleration is roughly to 9.8. Next, we also did a parameter about the frequency, but the length we changed it to 12 cm. And as you can see in this chart, the amplitude is increasing, and this fitting line also shows positive correlation. And we compare it also to the effective acceleration, and you can match it. The highest amplitude matches to the lowest effective acceleration. And next is the frequency of 3.5 Hz. And the amplitude is also increasing and matches to the effective acceleration. Next is the frequency of 4 Hz, and it is decreasing. So after we did all of our experiment of frequency, we can draw the slope of the angle. And as you can see, 3 Hz has increasing amplitude and 4 Hz has decreasing amplitude. And others we are unable to consider. And last is we change our parameter of the string length. And the frequency of the pivot is fixed. So the dots symbolize different lengths of the string. And as I mentioned before, when the slope is positive, it shows increasing amplitude. And when the slope is decreasing, it shows decreasing amplitude. And if it's nearly zero, we are unable to decide. Last is our discussion. Since we use our device to control the collision, we have to also investigate the collision by manual. So this is our experiment. And it collides in a track of circle. And if we use tracker to track the data of the movement of the pivot, and we can see this. So why does the pivot point move so dramatically down? It's because we dive down for collision, so the lato-lato can move in a circle. Final is our conclusion. So as I mentioned, the acceleration of theta angle will be like this. So when the amplitude is increasing, the effective acceleration will decrease. So it can have a higher position. And when the amplitude is decaying, the effective acceleration increases. So it has lower position. And this is the mechanism, effective acceleration. So as I mentioned before, the maximum angle will matches to the lowest effective acceleration.
Okay, time is up.
Thank you.
Proponent, please ask questions.
Okay, I would like to ask you to turn to page 13. Is that 13? 13.
Just a second. You can go to the question.
Okay, what do you mean by movement of the pivot?
This is a pivot, right?
Yes.
And when the pivot will move like this.
Yes.
So
And
this,
I mean, what is the movement? Is it the velocity,
Y.
acceleration, or you mean the position?
like y-axis.
So the displacement on the y-axis.
Yes.
And what is the unit? Is it meters?
Sorry, we didn't have unit. Like we just want to symbolize the reason for this chart is we just want to symbolize the
So
track.
you just show me the relative displacement without
Yes,
unit.
relative.
Okay.
We just want to show the
Okay, so
relation.
then I want to ask you to turn to page 13. Okay, here you mentioned that you think the length of the string is constant.
Yes.
Is that true? Yes.
Like for 9 centimeter is consistent.
Okay. Okay. Next question. I want to turn to the next page. What is the this
Collision times.
collision? You mean
Like-
the first collision, second collision?
Yes.
So how many experiments have to conduct?
We conduct many experiments, so we have error bar as well.
Okay, and I want to see the experimental videos. Oh, maybe at first. Okay. I think the problem statement mentioned that we have to use the ball. And what about this part? What is this?
What do you mean by that?
What is this?
Huh?
What is
The
this
ball.
upon the ball?
It's a string.
No, I mean in the middle of the string and the ball. What's this?
Like we have to attach it. Like we have to.
Oh, okay. That's okay. And I think time's up.
Okay, time. Preparation time for the program. Okay, the opponent is given floor.
Greetings, I'm the opponent from Team Ridiculous. First of all, let's clarify the problem statement. Attach a ball to each end of the string and connect the center of the string to a pivot. When the pivot oscillates along the vertical direction, the balls start to collide and oscillate with increasing amplitude. Investigate the phenomenon. So I have some main focus to underscore is that the effect of collision in this phenomenon and the relevance between the frequency of the pivot and the amplitude. And these are some pros and cons. So the reporter has a detailed illumination of theory and quantitatively talking about the experiments. Also conducted experiments regarding different parameters. A good experimental setup for phase 1 of Lato-Lato. Nonetheless, there are still some areas for improvement, like they have no clear notation in a few pages, confusing graph about frequency, and using hints to discuss phase 2 of Lato-Lato, which is very difficult to evaluate. So in the following discussion, I predict that I will discuss about the movement of the pivot and the length of the string, if it is constant or not, since I maybe see some wave-like pendulum. And I think I will directly discuss with the reporter. So I want to ask you to turn to page 16. Okay, I think I remember in the graph, you can see this is amplitude, right?
Yes.
Okay.
No,
and
this is the angle.
okay, so you use the angle to manifest the amplitude.
Yes.
Okay, and why isn't it start with 0? Because the problem statement mentioned the ball start to collide and oscillate with increasing amplitude. So I think the start is very critical in this phenomenon.
Like we just want to show the the difference.
Okay, so to investigate the starting, like how do you spark this motion?
We use tracker to track the
No, I mean how do you spark this system? How do you motivate it?
Like I mentioned in our experimental setup, we use an device to control the.
Yes, I know how to oscillate the pivot, but I'm asking you how do you start the motion, because I didn't see a graph from 0.
Like we give an initial force to.
You give an initial force, but I don't think the problem statement have asked us to do this.
Then if we don't give the
we just have to oscillate the pivot.
Yeah, so if we oscillate pivot, we are giving force to let it to the pivot up and down.
So then your graph should start with 0, shouldn't it?
No, because we just want to show the motion.
So do you have appendix or something that has the graph start with 0?
Yes.
Okay, then show me.
We didn't put it into this PowerPoint, but the meaning of this graph is just showing that this amplitude is increasing and the difference of changing the amplitude.
Okay, I heard you saying that the amplitude is increasing, but I see a decrease here. And what if the time go further? If there is like some pendulum over here, like maybe like 2 period pendulum or maybe something, and maybe here's a steady state of amplitude, and because I didn't see the time go further. So
The reason we didn't do a very long time is because if we like expand the time, that as you mentioned, the lato will be very inconsistent and many uncontrollable issues will happen significantly.
don't you think the problem statement will? Don't you think this phenomenon we should investigate this phenomenon further?
Like the meaning of this chart is just showing the tendency. Like we investigate this and it has an increasing tendency, and that's it.
So you are talking about the like the beginning part of the system. You didn't talk about if the time go further.
No, because if the time go further, the phenomena will be like the same, but it will be affected by some uncontrollable factors.
But maybe we should investigate that uncontrollable factors. Maybe.
Like how,
How do we show that?
like
There are so many mathematical process to measure that. There are many like exponents to measure that. So you don't use them. You didn't utilize
we use
them.
that, but
So
we
what,
did.
what exponent or maybe mathematical process did you investigate the further motion?
As I mentioned, the theory we use to analyze the mathematical motion is the effective acceleration. So
Your theory did not describe the
yes,
motion later.
like for this chart we have time to 80, but as you can see, after some specific time, the motion will remain.
Is this condition the same as the previous one I saw?
The frequency is different.
Okay, so what is the frequency I saw in the previous?
Because this experiment we
It is 3
conducted
hertz,
is
right? 3 hertz. And the one you just showed me is 5 hertz.
Yes.
And I can see your theory mentioned that it is because the variation of the equivalence gravitational field. And so have you ever considered that the oscillation period of the pivot that matches the natural frequency of the lateral fault so that it will cause the resonance? So have you ever investigated this part? Because I think it is very like relevant to your theory.
But since the problem statement mentioned to investigate increasing amplitude, so we are putting our main focus on
Yes,
how
I mean,
amplitude.
but resonance can cause a very drastically increasing amplitude. So, do you investigate this?
Yes, like,
Okay, so
but
what?
it is not a main
No,
focus
but
of.
the problem statement
What
said that we
if-
should investigate the increasing amplitude.
Yes, so we measure the increasing amplitude,
Yes, so I think the resonance is for.
but the
so,
problem statement didn't mention about resonance effect.
Yes, but the resonance will cause a drastically increasing amplitude.
It is not the, it is just not the main factor we consider in our experiment.
Okay, so can you turn to the page that have the coefficient of restitution?
Yeah, sure.
Despite the coefficient of restitution, are there any other effects that make your theory don't run by up? I mean, like maybe another energy loss. Do you consider any of them?
There are many energy loss, like sound. When it oscillates, the energy, some of it transform into sound. Like you will hear the sound of collision. Right?
Oh, you mean it's transferred into the vibration of the air, right?
Yeah, and also like heat, when it collides, it generates heat, and also damping effect.
Okay, you mentioned the damping, so did you fit it in the same sine wave?
Like it is like a constant number in our theory.
You mean damping factor or damping ratio is the constant?
Damping, like vector, because
Where is the damping factor?
like you can consider it with the coefficient of.
But just as you mentioned, the coefficient is not the whole story. You have
So you can know how much energy transform into the.
no, but that is not all the whole story. Like for instance, in this graph, I can see if you mentioned that the length is consistent, but I don't think so because obviously there is many slacks and the slack cause the energy loss, and so you should fit it in the damped sine wave to investigate the damping instead of coefficient.
What can you rephrase your problem?
Okay, so here I see the wave-like pendulum, so I consider it as the slack. And just as you mentioned, there are diverse factors that cause the energy loss, including the slack. So your coefficient of restitution, I guess it can describe the slack. Can it?
No, but if you move the chart to like you like smaller,
No, you can't do that because your length will not go that.
So that is only because of unit.
that's only because of the unit. Like if you change it to meter, it's almost the same. Like you change the
So,
unit.
Only because we only
But-
do experimental with
but can you play the video?
Yes.
There's a wave on the strip. Did you see it?
only because
There's a wave.
No,
So,
it is. We didn't.
Obviously, there is the slack, and also your graph said it, and you didn't believe it.
Because like that is not the main factor to consider in our problem.
I think it is. I think it caused a lot of energy loss, but okay, that's okay. If you think it is not critical, then.
We assume the tension remains the same.
But obviously, there's slack. Did you see that in your experimental video? Have you ever seen your experimental video?
No, but we prevent this kind of things happen in our other videos.
So what is this video for?
Just to show the collision.
And can you show me the video without slack?
We didn't put it. Sorry, that's my bad.
Okay. So you said that the pivot oscillation is a simple harmonic motion, right?
Yes.
Okay. So can you show me the graph of pivot oscillation?
Sorry.
Can you give a specific number of the, we don't know what you're.
Okay, that's okay. Maybe I will start here. So you assume the pivot oscillation as the simple harmonic motion. You just with that. So
So wait. Like we just assume it like this.
yes,
This
so
is the problem.
yes, this is because you use the sinusoidal wave to manifest its motion. So I think you mean that it is the simple harmonic motion. And why can you make this assumption? Like, do you have any experiment to prove the motion of the pivot is like this? If you don't, and then the equation of motion is totally wrong.
This is a theory, so we are just assuming it, and we really put our data into calculation. And the angle of radiance is the result we get from those kind of formula.
So you didn't prove any of these assumptions.
Yes, we did. We calculate the data.
So
and we
show me
use-
the data. You didn't put it in your presentation again, right?
We like in the chart. Like, what do you mean? What kind of data do you want?
I want the maybe
So-
position, velocity, or acceleration of the pivot, of the oscillating pivot.
But since the problem statement mentioned, we are putting our main focus on the amplitude increasing.
But the motion of the pivot is pivotal because if you don't know the pivot oscillation, then your equation of motion, you cannot prove it, you cannot verify it, it is wrong.
No, we just that is to describe the phenomenon. And
Yes, you need. So you mean your equation of motion is describing the phenomenon, right?
we just observe it and we put our data into the theory, and those are the results.
Yes, and your theory, you didn't prove any assumption of your theory. Is that true?
No, but
Show me the if you proved it, then show me the
do
position.
you want explanation or what do you want?
I want the graph of the pivot oscillation. Maybe you have the position, maybe you have the velocity, maybe you have the acceleration. Can you show me?
Yes. Like about acceleration, this is the acceleration.
Is this the acceleration of the pivot?
This is like the
Effective acceleration.
yes, and we can calculate like
So
this.
this is a angle, and you mean is this the real data, or maybe
It's a real data. We
also
put
this is
up.
not a numerical solution, right?
No, it's not.
Okay.
I can explain it because like since we mentioned in the theory the effective acceleration we mentioned is equals to the gravity plus the omega times a, and a is the amplitude, and amplitude is fixed.
Time is up. The opponent, please summarize the discussion.
Okay, so I would like to summarize the discussion. So in this, I asked about the motion of the pivot, and my opponent refuse to give me any graph of the oscillating pivot, so which inhibit my inquiry into this phenomenon. And also, the opponent shows me the graph and also the experimental video. I told him that there is slack in his experimental video, but he refused to admit it, which is very ridiculous. And also the reporter didn't investigate the time further only because he thinks there is too many uncontrollable factors. But I think the problem statement told us to investigate the increasing amplitude, and he isn't sure about if the amplitude increase or maybe in the future it will decrease. So this will be my summary. Thank you.
Okay, the review of paper flow next question.
Both of you, why do you think that the length will change?
You mean parameter of
The length of the length of the
it won't change. We check it.
It will change. In his experimental video, we can definitely see the slack. The slack.
Okay, and if you want to improve it, how?
If I want to improve the slack, maybe we should describe the damping instead of coefficient of restitution, because the damping can better account for the energy loss.
Okay, and do you think that this is a 2D motion?
Like theoretical model, if we don't have like some spinning or
In
others,
your real experiments?
it's a 2D. Yes.
Yes, I think he conducted the experiment very well, so it is a 2D motion.
I don't think that's a 2D. I believe that that's a 3D motion because it will just move front and move back through the observation video. And how do you track the ball?
Like we track the center of the ball, and we use trackers.
Do you observe that the ball will spin?
No, because our device is very stable.
So can you go to the observation video? And do you think that the ball will spin?
Yes, the ball will definitely spin.
Yeah. So how do you think that you can track since it will spin?
I don't think the spin will affect the track. But if you want to investigate the spin, you can put the camera upper here, so you can track the spin. But it doesn't affect the normal track.
Because, okay. And then, what do you think that affects the most to make the ball become higher?
According to our theory, we think that effective acceleration contributes the most. Because if the effective acceleration,
Sorry, force or frequent?
if you mean frequent of what, like pivot or higher?
Both.
If you,
Frequent of the fluid.
can you say a percent?
Force is more important or the fluid of the.
Both are length are important, and we put it into
The equivalence of gravitational field and also the resonance.
Yes. Okay. And then, do you think? When do you think that the resonance will happen?
The resonance happens if the oscillating pivot frequency is 2 times natural frequency of the optical ball.
resonance effect. We didn't consider it into experiment.
Do you think it should?
Like, it doesn't mention in the problem statement, so we ignore it.
Okay, time is up. And preparation time for the review. Okay, review of this table as well.
Hi, I'm the reviewer of this problem statement, this problem. And this is the problem statement. Overview for the reporter. The reporter observation is the dynamics analyzing, and experiment method is measure the angle, and then data analysis using Tracker and Excel. The conclusion of him is that increasing amplitude cause effective acceleration decrease, and decreasing amplitude cause effective acceleration increase. And for the pros and cons for the reporter, they have enough chart to support their experiment and their clear definition, and then the clear focus on the parameters. But however, the reporter's body keeps covering the page numbers, and then there's no clear notation in a few pages, and didn't prove the assumption of the theory. And for the opponent, the pros are they pointed out the missed points of the reporter and pointed out the errors of the chart of the reporter. And the cons is that they failed to reach the consensus. And for the discussion review, the opponent asked, what does the pivot movement means? And the reporter means that the y-axis with no unit, but we think that they should include the unit. And the opponent asked, why isn't the chart initial velocity at 0? And they said that we just want to do a demonstration in the motion, and we think that we agree with the opponent that we should it should be controlled at the same start point. And the opponent asked, how did you motivate the device? And the reporter said we use a device to give an initial force, and we believe that it isn't the focus of the problem statement. And the next is that, did you investigate the resonance? And the reporter said, because it's not in the problem statement, they don't include it, but we believe that resonance is the main factor of this experiment. And the opponent asked, did you consider energy loss? The reporter said they did, but actually they didn't. They are just answering that how the energy loss, but however they didn't quantify it in their experiment. And the opponent asked, does weight on the string contributes to the energy loss? And the reporter answered that it's not the main factor. And also we asked, what do you think it will change the length? Why did the length change? The opponent said that the length will definitely change, and the reporter said no, since what they observed and what their data is. But we think that the length will change is because the tension is too small. They should use a better material of it, like plastic. And we asked that is that a 2D motion. Both of them answered yes, but we believe that it's not. It's a 3D motion, since it will in their observation video it will move forward and move back. Thank you.
Concluding remark. Reporter.
This is our concluding remark, and the reporter really wants to restate that the length of the string is the same, and we have data. And also, if you really want to consider the string length changing, the tension of the string is not very significantly big. And also, to the discussion of our up and down position, even if we use manual to use the lato-latos, it could still be zeroized to the theory. And next is we use angle to present the amplitude of the lato-lato, and we didn't use x, y coordinate to present is because the y will be affected by the pivot movement. And the frequency has a more dominant effect than other factors. It will affect the critical condition to climb upward. And damping resonance effect can be neglected, like it is not a very significant main cause of this effect. As I mentioned in the theory, the main cause of this effect is effective acceleration. And effective acceleration contributes to the speed of the experiment, and as I said in the theory, when the amplitude increases, the effective acceleration decreases. Because if the acceleration decreases, it will allow the ball to move to a higher position. And also, phase 2 of manual experiment result fits our theory. And this is the end of our concluding remarks. Thank you.
Okay. Questions?
Very interesting. The opponent at one point said that the figure should be oscillating at twice the natural frequency of the pendulum. That's your point, right?
Yes, that's my point.
Of course, you know too much too. The reporter, in conclusion, still maintained that resonance is not important. This is, seems to me puzzling, because whenever it can increase, it's in resonance. That should be the case, right?
Yes.
And that frequency may not be the same as the natural frequency twice. The reason, do you know why?
Yes.
Any of you?
May I use the blackboard?
No, just very.
Oh, okay. Because when we say the normal natural frequency, it is like a simple pendulum, but in the lato-lato, this case, the one period is there is a collision, so the path of the ball is half of it, so the natural frequency should times 2.
But from its equation of motion, from the Newton's equation he used, where does that come in? It should come in. The Newton's equation, second law, right?
Yes.
He used, actually, this is the driven oscillator, right? The pivot provide the driving force. The pivot
provide a driving
force. Yes. This is not a natural oscillation. This is driven. The frequency of the pivot is omega. The natural frequency, what is it? You should first state that what's the natural frequency without pivot moving. There should be, usually, that's the simple pendulum frequency. Now, this question is a very good question for driving oscillation, because if you check the frequency, which makes it the amplitude increasing, it's usually not the natural frequency of the single pendulum. It's not. I can tell you 500. It should be. You should look at your equation of motion. You know what equation of motion will mean. Theta double dot. The second, the angular acceleration equals to your effective index. Your effective index is oscillating. It has a frequency. And then you also has the sine term in addition. Right? You show that's where you understand this whole phenomenon. And I think the transient behavior actually is not important. It's there, but that shouldn't be an issue. Because this is driven oscillation. It's the steady state. It's not the transient, where you fit the initial condition. That's I don't think. Maybe I am too This is a driven, you mean, you know, driving, you know. This is driven oscillations. Eventually, the system will respond to the driving frequency. This is general phenomenon of driven oscillation. But depends on what's the driving force. The driving force, if you look carefully, if the amplitude, the driving term, the amplitude is constant, then the frequency has to be the same. It is simply mathematical, very easy to justify. But this will affect acceleration against oscillation. That is actually there are no two periods. One is twice omega, the other is the constant. The constant will go on, but the frequency twice. That's the resonance. That's what makes the amplitude increase. You should understand that. It is not TV school, for TV school, but for physics. You all should understand. Look at your equation of motion. And all your answers should be based on this. That is, initial condition not important, which you can insist, which the others seems to be very concerned about. But since this is a steady state, it's the steady state. This equation just shows the character of the system. It's a driven system. The driven system always consists of two solutions. You probably don't know it. One is a complementary solution, the other is a particular solution. The particular solution is what we are talking about. That is this.
Okay, any other question? We have time. Is there any other question? Oh, no.
The theory is beyond high school.
Come to the scoring time of the journal. Okay, ready? For the reporter, 6, 6, 7, 7, 6. For the opponent, 8, 8, 7, 7, 6. For the reviewer, 8, 7, 6, 6, 5. Okay, this morning final ends. Thank you, everyone.